So imagine you're pushing a high-performance hybrid dual-motor vehicle down an open stretch of highway.
Okay.
You're hitting top speed, the powertrain is humming, and, from the driver's seat, everything feels perfectly dialed in.
Right. It feels smooth.
Exactly. But deep inside that chassis, invisible to you, there's this massive dual-motor control system that is aggressively managing just, violent amounts of electrical energy.
Oh, yeah. Massive amounts.
And in this extreme operational envelope, two critical safety protocols wake up.
Mm-hmm.
One protocol is looking at the temperature gauge, realizing the hardware is getting dangerously hot, and it wants to cut the power to cool things down.
Makes sense.
Yeah, but then the other protocol is watching the internal voltage, realizing the electrical pressure is spiking, and it needs to keep power flowing in a very specific way to prevent a blowout.
Right.
So suddenly these two systems, which are both designed to save the car, they start fighting each other.
It's a terrifying scenario from a systems engineering perspective, honestly, because what you're describing is a direct clash between thermal reality and electrical physics.
Right.
And if the vehicle's computer can't arbitrate that fight in, a matter of milliseconds, the resulting failure isn't just a software glitch, it's a physical, violent event.
Which is exactly why we are jumping into this today. We've got a really fascinating stack of sources on the table for this deep dive.
Some heavy reading.
Very heavy. Engineering white papers, functional safety specifications, and ASIL D teardown reports. Specifically, we are looking closely at the functional safety architecture for energy management and multimodal coordination.
Right.
And our entire focus for this deep dive is unpacking one highly specific, incredibly dangerous hazard known in the documentation as core fault E6.
Core fault E6, yeah.
The thermal and voltage derating logic conflict.
Wow.
Yeah. We're going to explore how this happens, how engineers build, microsecond referees to catch it, and the almost obsessive lengths manufacturers go to in order to ensure this conflict never makes it out of the factory.
The stakes here really can't be overstated.
No.
This logic conflict, it dictates the longitudinal dynamics of the vehicle.
Right.
If the system fails to manage this dual derating scenario, you're looking at unpredictable, violent torque variations that can, physically shatter a drivetrain.
Jesus.
Yeah. Or, alternatively, you get sudden high-voltage spikes that will instantly vaporize the vehicle's power electronics.
Vaporize them.
Literally.
Oh, okay. So to understand how engineers solve a problem this complex, we need to understand the battlefield first.
Right.
So let's look at the root cause analysis from these engineering reports. Why do these systems end up at each other's throats in the first place?
Yeah, why are they fighting?
Right. And the documentation points to four main triggers.
Okay.
And the first one is purely physical. It's this extreme speed antagonism.
So let's ground this in the physics of an electric motor for a second.
Please.
When the rotor inside the motor spins, its permanent magnets sweep past the copper coils of the stator. By Faraday's law of induction, that spinning magnetic field generates a voltage that pushes back against the battery's voltage.
Okay, I think I remember this from physics class.
Right, we call this back electromotive force, or back EMF.
Back EMF, got it.
So at normal commuting speeds, the battery voltage is higher than the back EMF, so power flows into the motor smoothly. Everything is fine.
But at extreme speeds, like say when the motor hits 12,000 RPM, that back EMF scales up linearly with the speed.
Oh, exactly.
So it naturally surges way past the physical limits of the vehicle's DC bus voltage,
It does.
generating more electrical pressure than the internal components can actually hold.
Right. And so to prevent the voltage from overpressurizing and, destroying the system, the motor controller relies on field-oriented control.
FOC.
Yeah, specifically a technique called flux weakening.
Okay.
This is the absolute core of your voltage derating strategy. The controller intentionally injects a negative direct axis current, which we call negative ID, into the stator.
Right, so it's essentially projecting an electromagnetic counterfield.
Exactly.
It creates this invisible shield that suppresses the permanent magnet's field, which keeps that back EMF voltage clamped down to a safe level.
That's a really great way to visualize it. A shield.
Yeah.
But maintaining that electromagnetic shield requires a whole lot of current.
Oh, I bet.
And pushing massive current through copper wires generates severe resistive heating.
Right, friction, basically.
Yeah, known as copper losses. So as you're flying down the highway, the stator windings are getting hotter and hotter and hotter. Once the temperature crosses a critical threshold, which is usually around 130 degrees Celsius, the thermal management system wakes up.
The other bouncer.
Right, the other bouncer. And its prime directive is to protect the insulation on the wires from literally melting.
Wow.
So it triggers thermal derating, and it starts forcibly lowering the total current limit.
And here is the fatal overlap.
Yeah.
Because I was reading this and it's like, the total current is a budget,
Yeah.
right? It's made up of the torque-producing current that moves the car and that negative ID shielding current that holds back the voltage.
Exactly.
So if the thermal derating logic is poorly written, it might blindly slash the total current budget so hard that it accidentally starves the shield.
That is the exact moment of failure.
Man.
If there isn't enough negative ID current left to maintain the flux weakening, the electromagnetic shield drops.
So the motor is still physically spinning at 12,000 RPM.
Exactly. And without the shield, the back EMF instantly breaks loose. We call this uncontrolled generator mode, or UCG.
So wait, how fast does that voltage spike happen once the shield drops? Like, are we talking seconds?
Milliseconds.
Wow.
A massive voltage spike, easily exceeding 1200 volts, slams back into the inverter.
Jeez.
It immediately punches through the dielectric breakdown limits of the silicon carbide modules and the film capacitors.
Those toast.
The electronics are destroyed before the driver even realizes anything is wrong.
All because the car tried to cool itself down.
Yes.
That's just wild. So that's the primary physical conflict, but the sources also detail a secondary root cause, and this one is related to the vehicle's architecture.
Right.
Because most high-performance hybrids use a traction motor and a generator motor, and they share a single DC bus and capacitor,
Yeah.
which creates what the papers call a desync interference.
Yeah, so when you have two massive electrical loads pulling and pushing pulsed power on the same exact bus, they generate high-frequency voltage ripples.
Okay.
It's basically electrical noise.
Right.
And to manage this noise, engineers designed the two motor controllers to run their pulse width modulations 180 degrees out of phase.
Like noise-canceling headphones.
Pretty much.
One sine wave peaks, while the other hits a trough, and they effectively flatten the electrical ripple out.
That is the intended design, yeah.
Okay.
However, the microprocessors controlling these modulations run on their own internal clock cycles.
Right.
And over time, or under heavy computational load, those clocks can experience a microscopic slide.
They drift.
Exactly. If the timing shifts by even a fraction of a millisecond, the modulations drift out of phase.
So the waves start to align.
Yeah.
When the peaks of the high-frequency switching ripples from both inverters hit the shared bus at the same exact time, you get constructive interference.
Yes.
The amplitude of that voltage ripple instantly doubles.
Which unleashes total chaos in the control logic.
I can imagine.
Because the voltage control loop detects this massive doubled ripple and immediately tries to execute voltage derating to suppress it.
Right.
But simultaneously, a doubled ripple generates erratic eddy currents and excess heat.
Oh, so the other system wakes up.
Right. The thermal loop detects the sudden temperature spike and tries to execute thermal derating.
And they fight.
Because the two loops lack a unified dynamic power allocation protocol, they fight over the current limits. They wildly adjust the power up and down at super high frequencies.
And because current directly correlates to magnetic force, these rapid current fluctuations translate into massive torque pulses. The driver feels that as violent mechanical shuddering tearing through the drivetrain. It's like the car is trying to tear itself apart.
It literally is.
Right.
Which leads us directly into the third root cause, which is priority inversion within the software itself.
Okay.
This is a classic computer science vulnerability, but here it's playing out in a highly lethal physical environment.
Yeah, let's break down the timing of the software, because this was fascinating.
Sure.
Field-oriented control requires lightning-fast reflexes to manage the magnetic fields, right?
Absolutely.
So the primary control loop is executing every 100 microseconds.
It's always fast.
Super fast.
Okay.
But the temperature readings, because heat transfer is much slower than electricity, they run on a slower background loop, updating maybe every 10 to 20 milliseconds.
Right, and that dual loop architecture makes sense for efficiency,
Sure.
but it creates a huge vulnerability if the real-time operating system gets overwhelmed.
Like a bottleneck.
Yeah. Imagine the vehicle experiences a burst of high-load computing, like a traffic jam on the CAN bus due to sensor noise, or multiple minor diagnostic faults triggering simultaneously.
So the processor just gets bogged down.
It does. And in that congested state, the operating system might suffer priority inversion, where it fails to promote the critical thermal data to the high-speed loop.
Oh, no.
So the fast 100 microsecond loop doesn't get the updated temperature limits.
So the fast loop is flying blind.
Totally blind.
It's pushing high-power commands based on outdated safety limits, driving the system right into a thermal wall.
Exactly.
And by the time the OS finally clears the traffic jam and registers the new temperature, the violation is so severe that the system panics and triggers an immediate, uncoordinated system shutdown.
Which, at highway speeds, is incredibly dangerous.
Yeah, pulling the plug at 80 miles an hour.
Exactly. But perhaps the most surprising root cause identified in these functional safety teardowns isn't a software bug or a thermal miscalculation at all.
Yeah, this blew my mind.
It's purely mechanical.
The mechanical sabotage.
Yes,
Because a hybrid car still has an internal combustion engine, right?
it does.
Meaning the entire electronics bay is subjected to a constant, punishing environment of vibration, usually between 100 and 1,000 hertz.
Right. And those relentless vibrations cause microscopic movements in the low-voltage sensor connectors.
How microscopic are we talking?
We are talking about pins sliding against each other by just 10 to 100 micrometers.
Which is like less than the width of a human hair.
Exactly. It's tiny.
And that microscopic rubbing creates fretting corrosion.
Yes.
It basically grinds the metal, creating this insulating layer of oxidized debris on the contacts. And I read that this debris causes sudden, momentary spikes in electrical resistance across the connection.
Right. And since the vehicle's computers determine temperature by measuring precise voltage drops across those exact pins.
Oh, wow.
Yeah, a sudden spike in resistance from a microscopic piece of debris causes a microsecond signal drop.
So the data is instantly corrupted.
The analog front end interprets that signal drop as a massive instantaneous sensing bias.
The computer hallucinates.
It does.
Because of a dirty, vibrating pin, it thinks the motor just spiked to 200 degrees in a single millisecond.
Yep.
And so it erroneously triggers both the thermal and voltage derating protocols simultaneously, sending the logic into an absolute tailspin.
It's a cascading failure originating from a physical micromovement.
That is wild.
Right. When you combine all four of these root causes, the back EMF surges, the clock desync, the priority inversion, and the fretting corrosion, you realize just how hostile the powertrain environment really is.
So the question then is, how does the system catch this before the car explodes?
Right.
According to the safety specifications, engineers have to build an ASIL D architecture.
The highest automotive safety integrity level.
Exactly. And the critical metric they are graded on is the fault-tolerant time interval, or FTTI. For core fault E06, the system has 60 milliseconds or less to detect the logic conflict, arbitrate it, and render the vehicle safe.
60 milliseconds is a highly aggressive window.
The blink of an eye.
Less than a blink. To hit that, the architecture relies on a multi-layered defense strategy.
Okay.
The first layer is plausibility gating.
Plausibility gating.
Think of it as a dynamic referee constantly watching the power flow.
Okay.
Every 100 microseconds, the software calculates the physical direct current power entering the inverter from the battery.
Okay.
And it compares it against the electromagnetic alternating current power being consumed by the motor.
Because according to the laws of physics, those two numbers should match, right?
Yeah.
Minus a predictable amount of heat loss.
Exactly.
If there's a sudden mismatch, the referee blows the whistle. A conflict is happening.
Right.
But what is the referee's rule book? Like if the thermal bouncer and the voltage bouncer are fighting, who gets priority?
So the referee relies on a hard-coded golden rule of priority.
Okay.
The arbiter looks at the motor state. If the motor is spinning in the extreme high-speed zone, say over 7,200 RPM, and the sensors indicate critical heat above 125 degrees Celsius, the arbiter steps in and actively strips control away from the thermal loop.
Wow. It locks the flux weakening current.
Yes.
The negative ID shield gets absolute priority, and the thermal system is forbidden from reducing it.
Yes. But it still has to solve the heat problem.
Right, because it's still burning up.
Exactly. So the referee forces the thermal system to only cut the torque-producing current, the IQ.
Oh. That is such an elegant piece of logic.
Isn't it?
You sacrifice physical acceleration, so the driver might feel the car lose a bit of power.
Right.
But you reduce the total electrical load, which lowers the heat, all while guaranteeing the electromagnetic shield doesn't collapse.
Exactly. It's prioritizing electrical survival over mechanical performance.
That makes total sense.
But as robust as that software referee is, it still relies on the main microprocessor functioning correctly.
Sure.
What if the chip itself suffers a hardware fault?
Oh, right. Well, the sources outline a hardware failsafe for that, too.
Yes, they do.
The door checker dual-core setup.
Right.
Core 0 is the doer. It's running all the complex field-oriented control algorithms, the 100 microsecond loops, and the derating logic.
Mm-hmm.
But Core 1 is the checker, and it operates with complete independence.
Core 1 isn't running the complex FOC math at all.
Oh, really?
No, it's looking at the raw physical data from the current and voltage sensors, and it uses basic immutable physical laws like the conservation of stator flux
Okay.
to double-check Core 0's intended output.
So if Core 1 detects that the doer's math is going to push the system into a voltage spike, it doesn't even bother arguing with the software.
Yep.
It bypasses Core 0 entirely and triggers a dedicated system basis chip to physically block the pulse width modulation signals.
Exactly.
It kills the power in under 100 microseconds.
Which successfully prevents the conflict from destroying the inverter.
Awesome.
But it leaves us with a massive physical problem.
Uh-oh.
You've just cut power to a motor that is still spinning at 12,000 RPM on the highway.
Oh, right. The back EMF is still there.
Exactly. We need a safety fallback to handle the mechanical and electrical aftermath.
So the transition to a safe state is mapped out meticulously in these documents.
Yeah.
If the system is at a lower speed, it executes a smooth torque ramp down, limiting the reduction to 500 Newton meters per second to prevent mechanical whiplash that could snap the drive shaft.
Right, nice and gentle.
But if we are at the extreme high-speed threshold, over 7,200 RPM, that smooth ramp down is way too slow.
Too slow.
The back EMS will overpower the bus. So the emergency plan is a hardware-level intervention called a Stepwise Active Short Circuit, or ASC.
This is one of the most counterintuitive yet brilliant safety mechanisms in modern engineering.
Really?
Yeah, because when you lose control of the back EMF at high speeds, you have to put that massive electrical energy somewhere before it breaches the inverter.
But intentionally short-circuiting a motor at 12,000 RPM, I mean, active short-circuiting is incredibly violent on the hardware. My question reading this was, how do they manage the localized thermal load without instantly melting the stator coils?
Well, you're hitting on the exact mechanism that makes ASC work.
Okay.
The system intentionally fires the switching gates to short the motor windings together.
Whoa.
First, it shorts two phases for roughly 1.5 milliseconds.
Okay, why just two?
This is a critical buffer. It absorbs the initial asymmetrical shock and prevents a massive instantaneous current surge that could shatter the rotor.
Oh, mechanically shattering.
Yes. Then, after that buffer, it shorts all three phases.
Creating a closed electrical loop entirely inside the welder.
Yes. By shorting the phases, the massive voltage generated by the spinning magnets has no path back to the fragile inverter.
Right.
Instead, that energy is locked inside the robust copper windings of the stator.
Sure.
And the copper has a significant thermal mass.
If heavy.
Very heavy. So the electrical energy is converted into massive amounts of I²R joule heating inside the copper coils.
Oh, I see.
The system essentially uses the heavy mass of the motor as an emergency heat sink, safely absorbing the energy while strictly clamping the DC bus voltage to 720 volts or less.
So it deliberately superheats the heavy copper to protect the fragile silicon carbide microchips.
Exactly.
It's an incredible brute force failsafe.
It really is.
But, catching a glitch in 60 milliseconds with active short circuits is still a reactive band-aid.
True.
The real engineering mastery is found in the DFMEA, the design failure mode and effects analysis.
The blueprint.
Right.
Yeah.
Like, how do we build a system that doesn't trigger these fatal logic conflicts in the first place?
The design phase is where they structurally eliminate the vulnerabilities.
Okay.
On the software side, beyond hard-coding the priorities, they have to ensure the control loops never act on bad data.
Right.
As we discussed earlier, when a motor gets hot, the physical resistance of the copper windings increases.
Right, because of the heat.
Yeah, sometimes by up to 40% at high temperatures.
Oh, 40%?
Yes. So if the software assumes resistance is a static number, its calculations for torque and voltage drift further and further from reality as the motor heats up, eventually triggering a false conflict.
So the source material talks about engineers solving this using 2D lookup tables and recursive least squares algorithms.
Right.
How does that keep the math honest?
A 2D lookup table, or 2D LUT, is essentially a pre-calculated map embedded in the software.
Okay.
Instead of the processor wasting precious time calculating complex thermal physics during its 100 microsecond loop,
Dang.
it references this table, which maps exactly how resistance changes at specific temperatures and frequencies.
Oh, so it's an instant reference guide for the computer.
Exactly. Well, sorry, to be more precise, it works in tandem with the recursive least squares algorithm.
Okay, what does that do?
While the LUT provides the baseline map, the recursive least squares algorithm acts as a real-time adaptive filter.
Okay.
It constantly compares the expected resistance against the actual voltage and current behavior.
Oh.
And it dynamically tunes the internal model to match the physical reality of the motor, even at 150 degrees Celsius.
That's incredibly smart.
It is. This dynamic mapping keeps the torque estimation error strictly under 3%. The software never panics because it always knows exactly what the hardware is doing.
So the software's perception of reality is bulletproofed.
Basically.
But what about the physical hardware vulnerabilities? We talked about the fretting corrosion earlier.
Right.
Engine vibrations causing micro-abrasions on the pins that trick the system into seeing phantom temperature spikes.
The hardware solution there is a testament to the fact that sometimes you can't outcode physics.
Yeah.
You just need better materials.
Ah.
Engineers upgrade 100% of those low-voltage sensor terminals to gold-plated specifications.
Which feels almost analog compared to all the advanced algorithms we've been talking about.
It really does.
Just make the metal out of gold so it doesn't rust when it shakes.
Uh-huh.
But gold is a noble metal. It fundamentally resists oxidation.
That's the core of it. Even under constant 1,000 hertz vibration and brutal thermal cycling, the gold plating prevents that insulating layer of oxidized debris from ever forming.
Wow.
It locks the contact resistance at a microscopic 1 to 3 milliohms. Those microsecond signal drops simply stop happening.
That's amazing. And the functional safety specs also highlight major upgrades to the analog front-end circuits.
Yes, they do.
The paper specifically emphasizes the use of Class 1 C0G ceramic capacitors.
Right.
I know capacitors filter electrical noise, but why are these specific ones mandated? Like, why are they so special?
It comes down to dielectric stability.
Okay.
Standard capacitors suffer from thermal drift, meaning their capacitance changes as the ambient temperature swings.
Oh,
They also exhibit piezoelectric effects, meaning physical vibration can actually induce false electrical noise.
Oh, so the shaking creates fake signal.
Exactly. Plus, 1 C0G capacitors are engineered with a specific ceramic dielectric that makes them almost completely immune to temperature changes and physical stress. They refuse to drift, ensuring that the analog signals remain flawlessly accurate before they are even digitized.
Okay. And to solve the desync issue, where the two motor controllers drift out of phase and double the voltage ripple,
Right.
the DFMEA mandates a synchronized hardware architecture.
Yes.
Instead of relying on independent chip clocks that can slide under heavy loads, all the microprocessors, analog to digital converters, and communication chips are physically hardwired to a single high-precision clock source on the circuit board.
That shared heartbeat is absolutely crucial.
Yeah.
It keeps the phase error between the two motor modulations locked to less than 0.5 degrees.
Wow, less than a degree.
Yep. Structurally eliminating the constructive interference problem at the hardware level.
So the blueprint is essentially a masterpiece of material science and adaptive algorithm.
It really is.
But, translating a perfect DFMEA blueprint to a messy assembly line is where the PFMEA comes in.
The process failure mode and effects analysis.
Right. Like, how do they guarantee these incredibly tight tolerances when they're actually manufacturing thousands of these units?
The manufacturing rigor is just staggering.
Yeah.
It begins at the end of line, or EOL, test bench.
Okay.
Before a dual motor controller is cleared for shipping, the automated test system connects it to a dynamometer, forces it up to the 12,000 RPM maximum speed,
Right.
and deliberately injects a fake 150 degrees Celsius temperature signal into the sensor pathways.
They actively try to induce core fault E06 on the assembly line to prove the logic arbiter prioritizes the negative ID current correctly.
Exactly. If the system fails to maintain the flux weakening shield, or if the torque transition isn't perfectly smooth, the unit is immediately flagged and scrapped.
Just thrown out.
Gone.
Yeah.
But the functional testing is just the final step. The component level inspection is where the real obsession with quality control shows.
Tell me about it.
After those complex Dewar-Checker microprocessors are mounted to the circuit board, 100% of the units are run through 3D automated X-ray inspection, or AXI,
Okay.
and scanning acoustic microscopy, or SAM.
Now, X-raying ball grid array solder joints is pretty standard for high-end electronics manufacturing.
Sure.
You have to see under the chip. But the tolerance listed in this safety spec is what really caught my eye.
The voiding limit?
Yeah, they enforce a strict 1% voiding limit for any individual solder ball.
It's intense.
Finding air bubbles that small is incredibly meticulous. Why are they so strict about 1%?
It's meticulous because of the thermal and vibratory environment.
Okay.
If you have even a 2 or 3% air void inside a solder joint, the constant 2000 Hertz engine vibration, combined with the extreme heat cycling, will eventually turn that microscopic bubble into a thermal fatigue microcrack.
Oh, wow.
That crack increases resistance, causing a signal drop, which tricks the system into a false derating fault, leaving the vehicle stranded.
Just from a tiny bubble.
Right. They enforce that 1% limit to prevent a failure 5 years and 50,000 miles down the road.
That attention to detail extends to the physical assembly as well.
It does.
Even with the gold-plated pins, the PFMEA demands an extra layer of protection against fretting corrosion.
Yeah, the grease.
Automated robots equipped with UV vision cameras inject a highly specific anti-fretting conductive grease, Niogel 760G, directly under the pins.
Right.
The UV cameras scan the connector to verify total coverage without any overflow that could short adjacent pins.
And to protect against electromagnetic interference, the grounding architecture is strictly controlled.
How so?
The grounding wires for the low-voltage sensor harnesses are ultrasonically welded in a full 360-degree ring around the connectors.
Wow.
This establishes a perfect Faraday cage, clamping the grounding resistance to under 10 millions, ensuring high-voltage switching noise can't corrupt the temperature data.
We also have to consider the high-voltage bus bars.
Oh, right.
Those thick copper plates carrying hundreds of amps of current. The bolts holding those bus bars together are a massive failure point, right?
Huge.
If a bolt is even fractionally loose, that high current arcs across the microgap, creating localized Joule's heating that can literally melt the surrounding plastic housings.
To eliminate human error there, the factory uses computerized servo screwdrivers.
Okay.
These tools are far more advanced than standard torque wrenches. They continuously measure the torque-to-angle curve as the bolt is driven into the metal.
So they're essentially calculating exactly how much the metal of the bolt is stretching.
Yes. They stretch the bolt just past its yield point so it acts as a permanent mechanical spring.
Oh, that's clever.
Yeah, maintaining immense clamping force despite thermal expansion and contraction. The servo screwdrivers must keep the final clamping deviation within plus or minus 3%.
And finally, to verify the software, the factory uses cryptographic security.
Right.
When the complex parameter files, including those critical 2D LUT resistance maps we talked about earlier, when those are flashed onto the chip, the system generates a SHA-256 hash.
Yep.
It mathematically proves that the code on the physical hardware matches the master engineering file down to the exact bit, preventing a corrupted parameter from ruining the thermal math.
It is a remarkable convergence of disciplines.
It really is.
You have UV-guided robotics injecting grease, automated X-rays hunting for microscopic air bubbles, servo screwdrivers precisely stretching steel, and cryptographic hashes verifying control algorithms.
All of it orchestrated just to make sure a dual motor system spins safely.
Exactly.
But, even a perfectly manufactured unit still has to prove it can survive the real world.
Right.
Before this architecture goes to the consumer, it enters the DVP&R phase.
The design verification plan and report?
Or, as the industry treats it, the torture testing phase.
Absolutely.
The sources detail a 100,000 cycle thermal hell test.
Thermal hell is the right name for it. The goal here is to simulate a lifetime of extreme abuse in a highly compressed time frame. Engineers place the completed power control system into an environmental chamber set to an ambient temperature of 105 degrees Celsius,
Okay.
while simultaneously pumping 85-degree coolant through its internal channels.
So the hardware is effectively boiling.
Basically.
Then they spin the dynamometer up to the 12,000 RPM threshold and inject that 150-degree fake temperature spike directly into the software.
They force the system into the core fault E06 logic conflict 100,000 consecutive times.
Wow.
And the passing criteria are absolute.
What are they?
There can be 0 uncontrolled generator faults, 0 overvoltage alarms, and the permanent magnets inside the rotor must show 0 irreversible demagnetization from the extreme heat and current.
That is strict.
Furthermore, Every single time the arbiter steps in to smoothly transition the torque and lock the shielding current, it must complete the entire operation in less than 10 milliseconds.
Which is an incredibly tight operational window for a system under that much thermal stress.
It's intense.
But they follow that up with mechanical torture, too, the shake and bake test.
Oh, yeah. Following stringent ISO standards, the control unit is clamped to an electrodynamic shaker table.
Okay.
It is violently vibrated across 3 axes at frequencies up to 2,000 hertz, pulling intense G-forces.
Wow.
And while it's shaking, the thermal chamber violently swings the ambient temperature from negative 40 degrees Celsius up to positive 125 degrees Celsius.
And they hold it in this state of combined thermal and vibratory agony for over 1,000 hours.
1,000 hours.
The fascinating part is how they grade the test. Because passing isn't just about plugging it in and seeing if it turns on right.
No, functionality isn't enough at all.
What do they do?
After the 1,000 hours, engineers perform a destructive physical analysis.
They cut it open.
They literally section the microchips, slice the circuit boards, and examine the internal layers under scanning electron microscopes.
Wow.
They have to structurally prove that the brutal testing didn't initiate a single fatigue micro crack in the solder joints.
Incredible.
And that the circuit board layers show 0 signs of delamination.
They cut it open to prove it didn't even begin to fail.
Exactly.
It is a level of dedication that is hard to wrap your head around.
It really is.
But the final validation test takes us out of the physical lab and into the virtual matrix.
The HIL test.
Right. The hardware-in-the-loop load dump simulation.
This test validates the absolute worst-case emergency fallback.
Okay.
Engineers use high-fidelity FPGA simulators to create a perfectly simulated virtual powertrain.
Right.
They connect the physical, real-world engine control unit to the simulator and subject it to a catastrophic scenario.
The setup for this simulation is basically a nightmare.
It is.
The virtual motor is spinning at 12,000 RPM. Suddenly, the system simulates a physical relay failure, causing the high-voltage battery to completely disconnect from the DC bus.
The load dump.
Right, the load dump. The motor's pushing maximum back EMF, but the battery, the primary place for that energy to go, has vanished.
Vanish.
And at that exact same microsecond, they simulate a broken temperature sensor, feeding the system a fake thermal emergency.
It is the ultimate logic conflict combined with a massive hardware failure.
Right.
The ASIL D architecture has exactly 60 milliseconds to navigate the chaos.
Oh, man.
It must recognize the battery disconnection, realize the standard smooth torque ramp down is impossible, and immediately trigger the Stepwise Active Short Circuit.
It'd have to instantly pull the trigger and short the stator phases.
Exactly. The simulation proves that the physical ECU can reliably execute the ASE timing perfectly, clamping the massive voltage spike below 720 volts and keeping the internal short circuit current strictly under 550 amps.
Wow.
Allowing the thermal mass of the copper to safely absorb the load.
Just incredible.
And what's truly remarkable is how engineers prepare for this.
Yeah.
Long before a physical prototype is even built, they develop advanced Python models to simulate these exact electromechanical transients.
So they game it out beforehand.
Right. They model the PID controller delays, the constructive ripple interference, the precise thermal drift of the sensors.
Wow.
They mathematically tune the safety margins and arbitration logic in a purely virtual space to near perfection before physical testing even begins.
When you step back and look at this entire deep dive, the sheer scale of the engineering is staggering.
It's massive.
We just spent this entire time unpacking the solutions to one highly specific logic conflict, balancing high-speed electrical physics against thermal realities, all to execute a safety protocol in under 60 milliseconds.
Right.
From 3D X-rays and cryptographic hashes to 100,000 thermal shock cycles and intentional stator short circuits.
It really pulls back the curtain on the invisible complexity that keeps us safe on the highway.
Doesn't it?
We interact with a pedal and a steering wheel, completely unaware of the multi-core, high-frequency arbitration happening just inches away.
It is a masterclass in control systems. But before we wrap up, you brought up a really compelling thought while we were reviewing the functional safety specs earlier, and I think it frames this entire discussion perfectly.
Yeah, it comes down to the trajectory of systems engineering.
Okay.
We just spent an extensive amount of time exploring the agonizing lengths, the dual-core validation, the microscopic material science, the algorithmic filtering.
Right.
All required to arbitrate a conflict between two strict, unambiguous laws of physics. Do not overheat and do not overvoltage.
Right. It's incredibly complex math, but at the end of the day, it's still just math.
Yes.
The variables are physical and measurable.
But as the automotive industry rapidly transitions toward full autonomy and artificial intelligence, the control systems won't just be balancing physics.
That's a good point.
They will be tasked with arbitrating highly ambiguous, chaotic variables, unpredictable human traffic behaviors, degraded road conditions, and complex decision-making scenarios where the right answer isn't a mathematical certainty.
Right, like what to hit if a crash is unavoidable.
Exactly. If it takes 3D X-rays, 2D lookup tables, and cryptographic verification just to safely prioritize temperature versus voltage, the engineering required to build priority gating for the unpredictable chaos of autonomous driving in real time is going to be a monumental challenge.
It is the next great frontier for functional safety.
We've mastered the physics, now we have to engineer the logic for chaos.
That is definitely something to think about the next time you hit the highway and let the adaptive cruise control take over. Thank you for joining us on this incredibly deep dive, and we'll catch you on the next one.